on alternating current circuit. Okay, the introduction of this AC. Okay, we'll begin with the outcomes, the introduction of the AC and what is sinusoid and phasor relationship with sinusoid and else. And in the end of this chapter, we'll cover on impedance. What is impedance? Okay. As for today, we will only cover until here. Okay. So the next part is tomorrow. Okay, let's start. So the outcomes of this chapter is you must be able to convert time domain sinusoidal voltage and current to phasor notation and vice versa. Represents circuit using impedance, solve steady state AC circuit using phasors and complex impedance. It is a complex number. Usually impedance is written in complex number. Learn complex power notation, compute apparent, real and reactive power for a complex load. Okay, in DC we don't consider this complex load. Draw the power triangle and compute the capacitor size required to perform power factor correction on a load. Okay. So as for introduction, by the way, can you hear me?
Yes.
Yes, very clear.
Okay. As for introduction, so in this chapter we only focus on AC. I think you know what is AC. Okay, the sine wave voltage, the current. Okay, the sinusoidal current is usually referred to as alternating current. So we call it alternating current because it alternate from positive to negative, positive, negative. So in DC it's only positive or negative DC. Okay, it's not alternating. Okay, as for the symbol, maybe in the in general, so yeah, it looks like this symbol for AC source. Okay, as I mentioned just now, it alternate from positive to negative. Okay, in one cycle in Malaysia, do you know what is the frequency of AC voltage in Malaysia? Anybody?
50.
50. Okay, in the world there are only two.
12.
Huh?
12.
12 what? What 12?
Voltage.
Voltage no? Are you kidding? Are you joking? Okay, in Malaysia, it's 50 hertz. Okay, so if you go overseas, you want to buy some electrical appliances, make sure you buy maybe the charger or whatever, return this one. Okay, don't buy 60 hertz. Okay, this is the other one in the world. No, but if in Japan you can use both. Okay, if in Japan you can use both. Both can be used because Japan. This is the Japan map. Okay, like this, separate. Okay, this side is 50 hertz, and the other side 60 hertz. Okay, due to the maybe different country, different Western country.
So as Japan went to?
Huh?
Why Japan did that?
Maybe in history they have different foreign country coming to their place. Maybe this one, I think in US, I think, or something related to US. Or the other one is UK related. Okay, so that's why it has two. And now it's even in power system, okay, the high voltage system transmission also. There are some point where they need to convert from 50 to 60 hertz at the border, okay, border somewhere, okay. East Japan and West Japan. So this is West Japan, and this one is East Japan. East. Okay. So in Japan, they have a lot of company, a lot of electrical company. I think around 9, if I'm not mistaken. 9 power provider. Okay, it's not like in Malaysia we only have one, which is TNB. In Japan they have 9, different for each region. Okay. So by the way, let's go back to our subject. So our frequency is 240. What is the voltage at the socket? Voltage? Anybody? Just now somebody said 12 volt. No, it's not 12 volt.
240.
Yeah, it's 240. 40 plus minus, I think 5%, if I'm mistaken. So the voltage will fluctuate. Okay. So the standard is 240. So it fluctuate 5%, plus minus 5%. Okay. So the other voltage in the world is 110 volt, which is in Japan. Maybe also in, I think in the US also. Okay. Okay. So 240 volt and 50 hertz. So if 50 hertz, this is a sine wave. One cycle, how long is one cycle? F equal to 1 over T. Okay, T equal to 1 over F. So one cycle is, try to calculate, or maybe you can guess. 1 over 50 hertz. How long?
0.02.
Yeah, 0.02 second or 20 millisecond. Okay, so half cycle is 10 millisecond. So for every 10 millisecond, the polarity will change, will alternate positive 10 millisecond, negative 10 millisecond. Okay. Okay. Okay, the circuit analysis is considering time varying voltage source or current source. Circuit driven is driven by sinusoidal current or voltage, are called as AC circuit. A sinusoid can be expressed in either sine or cosine form. Okay, in generating AC voltage, okay, there are one way to generate AC voltage. To generate AC voltage is to rotate a coil of wire at constant angular velocity in a uniform magnetic field. For example, like this image. Okay, we can generate, this is constant magnetic field, north and south. This is simple one. So we can generate AC voltage by this configuration. Okay, we have two ring here. Okay, at the 0 degree position, coil side move parallel to flux line. Since no flux is being cut, in this voltage is 0. Okay, this is at 0 position. The flux is this way, from A to B, from north to south. Okay, north to south. Oops. What is this? Okay, you have a magnet, so and S, this is the direction of flux. Okay, if you remember. magnet bar, and the direction of flux is from north to south. Okay. Okay, at this position, 0 degree, no flux cutting. Okay. So when it moves 90%, 90 degree, okay, it will cut the flux. So current will flow. Okay. Current will flow from one way because now the flux is like this. So this is the conductor and it moves 90 degree here. Okay, the flux is around it. Okay, so now I move till here at this position. Let's change color. Okay, move to here. So voltage will be generated. Okay. Okay, 90 degree. It's difficult to draw. Okay, at least 90 degree. So when it move down, okay, from 90 degree to 180 degree, okay, the voltage will drop from maximum to 0. Okay, the first 90 degree, next 90 degree, then this A conductor will rotate again 90 degree, then it will be maximum value here when it reach here. Okay, from here to here. Okay. This is at 270 degree, 90, 180, then go back to 0. Okay, so this is how the cycle looks like. Okay, so the different direction of current depends on the different current flow in the conductor itself, on this conductor. Okay, how to determine the current flow? I think you learned this in high school, or maybe matrix, or maybe STPM. I think it's high school physics. Any rules that you can think of? Any hands rule?
Left hand Fleming.
Left hand. Left hand related to force. The other one.
Right hand rule.
Yeah,
Right hand grip rule.
Yeah, right hand rule. This one, right? This is magnetic field direction. This is direction of current. Can you understand what I'm saying? What I'm explaining here? Try to understand. Okay. At the first position, 90 degree, the magnetic field is this way, right? The magnetic field is this way, from north to south. Then direction of current is this way, get inside. Okay, means that from A here, change color. Okay, so I move from here, from A here to this direction, then go inside. Is it right? It's from A. Yeah? Okay, so this direction, magnetic field is this direction. Current, so current should flow this way. Why? This one is while NA is positive. NA is positive. Hmm. Hmm? Wait a second. Why A positive? You can try to verify this figure. Try to verify this figure. Is it right or wrong, the direction of current? With right hand rules. The B, the blue one, okay, the blue conductor, this one, connected to this ring. A is connected to this ring. Okay, current flow this way. So which conductor we are looking at? B. If you're looking at B as the where the current is flowing, then the flow is right. Flow is this. Current go inside. The current is that way. But if we're looking from A point of view,
Follow the rotation, right?
rotation is this back rotation, right? So like this, follow the rotation. Initially it's like this, then it become like this. Never mind. You please verify later if try to understand this one. Okay, it's just using this one, this right hand rules. Okay, to determine the flow, the direction of current flow. Okay. Current flow inside. Okay, we proceed first. Okay, so basically that's how it works. Okay, let's take a look on the definition of the waveform. The first one is period. Period is the time taken to complete a cycle. Okay, this is period. Okay, period TS, one cycle. Peak value, the maximum instantaneous value measured from 0 to maximum. So this is peak value, VP. Peak to peak, maximum variation between the maximum positive instantaneous value and maximum negative. Okay, this is VP to peak. Peak is this one. Okay, from positive to negative. Okay, so you can see the variation of one cycle. This is clear one cycle. Okay, so it starts from 0 and ends from 0, but this one is not starting from 0. Start from here, maybe around 50% from maximum value, and it ends also at this 50%. Okay, and this one is start at maximum and end at the maximum. So that's one cycle. Must complete 360 degree. Okay. If you have any question, you can directly ask here. Okay, let's consider sinusoidal voltage. Okay, it is expressed in terms of time domain. Okay, Vt here. Okay, equals to V maximum, Vm, V maximum, or the amplitude. Okay, and then sine omega t, the argument of the sinusoid. Okay, omega is the angular frequency in radian. Okay, the sinusoid repeats itself every t second. Okay, the period t second. Thus, t is called the period of the sinusoid. Okay, or the time taken to complete one cycle. And this is equation how to convert f and t, relationship between the frequency and time, the period of the sinusoid. And omega is equals to 2 pi f or 2 pi over t. Okay, and then this is the most important part, which is the VRMS. Okay, VRMS is actually what we are always saying in our power system. Okay, the 240 volt is VRMS. Okay, at the socket, actually VRMS. Okay, omega is usually expressed in radian per second. Theta is in degree. 2 pi radians equals to 360 degree. So this is how to convert from degree to radian, or convert the other way around. Okay, radian to degrees. Just multiply these things, pi over 180, or to convert radian to degrees, multiply 180 over pi. Okay, if the waveform does not pass through 0 at t equals 0, it has a phase shift. Okay, as what is shown in this figure. This is with phase shift. Okay, this one without phase shift. Okay, it starts from 0. Okay, so when we have a phase shift, for example, if the waveform shifted to left, so we add phi, okay, plus phi. Okay, it's shifted right, minus phi. Okay, this is called a phase angle of a sinusoidal function. Okay, if it starts from 0, then equals to 0 lah, this part 0. Okay, so no phase shift. Okay, this is important concept. Okay, because we will see later how current can have a phase shift on voltage. Okay, so it's not in the same phase.
Sir,
Yeah.
what's the difference between shifted left and shifted right? I mean at the graph.
Yeah, you see this graph?
Yeah.
Yeah, this is shifted to the left. This one, left from 0 to the left, negative side, if you can think of that. Okay, from
So
0 to negative, so it's plus phi. It moves to the right from 0. If move here, like if I have another one like this, okay, this one is Vt equals to Vm sine omega t minus phi. Okay, move to the right is minus phi. If move to the left, negative.
Okay, sir. Thank you, sir.
Okay. The
Sir.
reference point is at 0.
Oh, okay, okay.
Yeah, reference is from 0.
So you refer to the zero.
Yeah, 0. 0 is 0 lah. No phase shift, no phase angle. Okay, from 0 to the left, negative. To the right, positive.
Sir, so the angle which is we need to take from the x-axis or y-axis?
Angle here is x. Y is the amplitude. This is the amplitude. Okay. This is time. Time, sorry, the angle, sorry, not time. Omega t is angle. This one, radian per second. Okay. This is not time. This is angle here.
So we
0 to
from the x-axis.
yeah. This is
Okay.
180. Maybe this one 270. Sorry, this 360. Sorry, 180. 360. Okay, this one 270. This one plus 90, 450. Okay. This is in degree. If in radian, then it's pi lah. Okay, the 360 equals to pi, and so on. You can change this one. Pi plus.
So maksudnya kita ambil yang penghujung one full circuit lah, bukan ambil permulaan dia. Dia punya
Penghujung
nilai.
What do you
Untuk
mean?
nilai the x-axis yang angle tu, maksudnya for the shift left, for the blue one, so the angle which is we take setulis 200 and something kan? Yeah, ambil
No. It's not like that. It's calculated from here, from the center, from 0. So if this value here is 270, meaning that is 3/4. 3/4 times 2 pi. 260 is 2 pi. Sorry, 2 pi. So 3/4 times 2 pi. Then this one is 3/2. 3 pi per 2. Means that shifted. Here it's shifted. Pi lah. Quarter pi. Half of pi. Pi over 2. So the pi here is pi over 2. Pi over 2. Paham? Understood? Let's see. Because the reference is in the middle, is 0 radian. Okay. So we see the difference. Here, this is pi per 2, pi, pi, 3 pi, then here is 2 pi. So we start from 0. We start from 0. From not really a 0 actually. Later we will see how. Maybe I need a better space to write. Wait a second. Okay, can you see my Jamboard?
Yes sir.
Okay. So for basic understanding, we put the reference starting from 0. Okay. This is reference. In some case, maybe the reference wave is not starting from 0. This is another case where it doesn't start from 0. Okay, but when we want to compare with another wave, for example, okay, compare with this one. For this one, this is current wave. Actually, this is the application, okay, of the phase shifting. This one is V. So we subtract these two, this one and this one, to see the phase different, to see the phase shifted, how far the phase shifted. This one by 2, this is by 1. Okay, to see the difference, so we can just minus, subtract this one, so we can see the difference. But in general, if we have equation Vt equals to Vm sine omega t plus, okay, for this one is 0. Okay, for the red one, Vt Vm sine omega t plus, because one is 5/2. Okay, for the blue one, this one is I t equals to Vm sine omega t plus pi. Okay, so can you see the difference?
Okay, sir.
Okay. Okay, let's move back to our slide. Okay, this is the example if shifted to the right, so it's minus here. Okay, that's what shown just now. Okay, let's take a look at the example. We have this sinusoid dt equals to 12 sine 50t plus 10 degree. Okay, find the amplitude. What is the amplitude? So here the amplitude is this one, the Vm is 12 volt, and then phase is 10 degree here, and angular frequency, which is the omega, 50 radian per second. The period of the sine wave, here t equals to 2 pi omega. Omega equals to 2 pi f equals to 2 pi over t. So just switch t and omega, we get this one, the period, and then the frequency is 1 over t. We get this one, so we can get this frequency. Okay, that's it. It's a simple example how to identify the elements of this equation, the sinusoid equation. Okay, second one. Yeah, I think it's the same. What is the frequency? Frequency. What is the period in millisecond? By the way, what is millisecond? 10 to minus What second?
3.
-3. Okay. What is the magnitude at V of V at T? Okay. Magnitude of V. So we just replace this one inside this equation. So we get the V. And then the RMS value. Okay. RMS value is V maximum, V peak. Okay. Over √2. Okay. Simple example.
Sir, RMS stand for what, sir?
Root means square. Root means square. Let me write here. RMS. It's written here. This one. Root means square. So, okay, it's this one. The maximum, the peak over √2. Okay, just remember this one. What is RMS? And how to convert it back to peak value if RMS value is given. So you can just multiply the square root 2. You will get the V max or the amplitude.
Alright, sir. Thank you, sir.
Okay. Okay. So here we have two sinusoids, V1, V2. The V2 is occurred first in time. Thus, it can be said that V2 leads V1 by phi. Okay, this is an important expression you need to understand. Or the other way around is V1 lags V2 by phi. Okay, depends on which point of view we are looking at. Okay, if we said that we're looking from V2 point of view, V2 this one, so V2, this is V2. Okay, from V2 point of view, V1 is lagging. Okay, so V2 is leading the V1. Okay, V2 is leading the V1. Okay, which one V2? Or wrong one? Not this one. Oops, sorry. V2 is the dotted line. Okay. So this one occurs first, then this one. We can say that V2 leads V1. Okay, because it starts first. Or V1 lags by V2. Okay, because it comes before after. Okay. If phi doesn't equal to 0, we can say V1 and V2 are out of space. This is the term that we use when there is a phase shift between two sinusoid. Okay, so like this one here is clearly out of phase. Okay, V1 and V2. If it is in phase, okay, it must be this V2 must also started from here. Started from center, yeah, from 0, or V1 must start here, the same where V2 started. Okay, so it's like this. This is in shape. Okay, in phase. When it's have shifted a little bit, so we say it out of phase. Okay, V1 and V2 can be compared in this manner because they operate at the same frequency. Okay, doesn't need to have the same amplitude. If different frequency, then we cannot say anything about their shift, phase shift. Okay, it must be one-to-one comparison, the same frequency comparison. Okay. Okay, then the comparison, the transformation between cosine and sine form. Okay, sine A. Okay, we can convert, we can transform into cosine A minus 90, cos A can be transformed into sine A plus 90 degree. I hope you can imagine what is cosine when what is sine wave. Okay, this is sine wave. This is sine wave. So cosines start from here. Okay, this is sine, sine, and this is cosine. Okay, converting from negative to positive. Sine A can be converted into sine A plus or minus 180. Or cosine also the same way, A plus minus 180. Okay, remember the x-axis is the angle. Okay, the phase angle. Okay, example 3. For the following sinusoidal wave of voltage, find the value V at t equals 0 and t equals 0.5. So yes, replace the value. Replace the t into this equation, you will get the voltage. Note that both omega t and phi must be in same unit. Okay, we cannot use if one is radian and the other one is in degree, we cannot add up. So we need to change them first into same unit. Okay, radian and radian, radian plus radian. Okay, degree plus degree. Okay, rad plus degree, no. Okay, calculate the phase angle between these two, between this V1 and V2. State which sinusoid is leading. Okay, so how can we compare this one? Okay, in order to compare V1 and V2, we must express them in the same form, either cosine or sine function. So here we have two different waveform, cosine and sine. Okay, with positive magnitude. Okay, note that phi must be between 0 to plus minus 180. So we need to convert them first. Choose which one we want to use. Okay. So for example, if you want to compare in cosine form, okay. So we convert it into positive first. Okay, from cosine negative, how we can convert to positive? Just use this one. So just minus 180, and we'll get the angle minus 130 degree for V1. Okay, and from V2, need to convert from sine to cosine, sine to cosine. Okay, use this one, minus 90. Okay, so we'll use minus 90 here, and we'll get 12 cos omega t minus 100. Okay, so we can compare now the phase different. Okay, this 130 and 100. So V2 equals to 12 sine omega t minus 10 degree equals to 12 cos omega t minus 10 degree minus 90. So V2 equals to 12 cos omega t minus 130 plus 30 degree. Okay, so we can see here, or we can just calculate it outside 130 because it's in the same polarity, it's negative, so minus 100, so it's 30 degree different. Okay, okay, in the above expression means that V2 leads V1 by 30 degree. Okay, so 30 degree, for example, be like this. This one is sine. Cosine first. Cosine. Okay. Okay. So one is at 100 degree. The other one is at 130 degree. Which one? This one is V1. V1, V2. Okay, so the difference is here is 30 degree. That's why we can say V2 leads V1 by 30 degree because it moved from V1 to the left. So it's leads. Okay, go back to this previous slide on how to determine which one is leading, which one is lagging. Which one? Where's the slide? Leading, lagging. Ah, here. Okay, this one. Okay.
Sorry.
Yeah.
I can understand that. Where does the 30 come from? The positive 30. Is the equation equation V2 equal to 12 cos omega t minus 130 and plus 30. Where does the plus 30 come from?
Okay, this one is to justify this one. Minus 130 plus 30 is minus 100, right? This one minus 100. Minus 100.
Oh, so it's just optional lah. If you want to write the V2 equal to 12 cos 130 minus 130 plus 30 to justify the equation above lah.
Yeah.
Oh. So if I didn't want to write it, it's also okay.
Yeah,
right?
okay.
Okay.
As long as you understand.
Okay, sir. Thank you, sir.
Okay. Okay, we will stop here. Tomorrow we'll take a look into phasor. Any question? Please do revision on this because this is I think new for some of you. Because next is much more complex. Okay, we'll get into complex number. Okay, if no question, I will stop here. Okay, seems like no question. So we end our class with Tasbih Farah.
Thank you, sir.
Okay.
Thank you, sir.
Thank you, sir.